So, as she said, I've been working in this field for about 4 or 5 years. The past couple, I've been freelance, and I would also not consider myself an expert at natural language processing. I'd say I've used it occasionally in different projects that I've done, both professionally and for fun. But I'm still, I guess I'd say I'm intermediate in my theory, my understanding of theory. That said, I chose this talk because I wanted an excuse to learn more about word embeddings and algorithmic fairness. So I'm going to try and take you along like the journey that I took over the past couple of months and just what I learned. So the hope is I can jumpstart all of you to get to a place where you feel more comfortable with those concepts. So this first came to my attention when I started seeing like this type of stuff in my Twitter stream. Oh yeah, on the previous slide, I should have pointed out for emphasis the slides, all the slides and all the code I talk about is up in that GitHub repo. But okay, in this slide we see something I saw more and more in my Twitter timeline, and this person just trained a word-to-vec word embedding using a Google News corpus, and they were just playing around with analogies, and they got some pretty misogynistic results. So in case you can't read it on the top, it says, "She is too persuasive as he is too eloquent, cogent, forceful, compelling, persuasive." All these wonderful positive synonyms for persuasive. And then they tried the opposite. "He is too persuasive as she is too unpersuasive, seductive, motherly, ditzy, manipulative." Like, I was blown away by that. Like, at the time, I had a good idea of how word-to-vec worked, like what it was, a vector representation of words and kind of encoding semantic meaning, and seeing that it was trained on, something that wasn't openly misogynistic and racist, I wouldn't think, that like really blew me away. And so that was just someone playing around with the word embedding. I also started seeing stuff like in production. So APIs that people were using. This is an example from the Perspectives API. And this person just started hitting the API with different text, and the point of it was the API gives you back a percentage of toxicity. And this API was trained on Wikipedia talk pages, and it's being used, I think it's still being used now, by the New York Times to help them automate their content moderation, their comment moderation. So it's just being used to flag toxic comments on their web pages for manual review. But when this person entered in these like identity phrases, they got some pretty concerning results as far as one group versus another. I also saw, it wasn't just one API, it was lots of sentiment stuff and the various flavors of sentiment. So across religious groups, they saw different positive and negative sentiment. And I also started to see lots of translation errors. And there's always been translation fails, but I started to see stuff powered, I assume, by neural translation. And this specific one, context mattered. So on the left, there is neutral and positive context, where the characters above were translated as black foreigner. And on the right, there were negative contexts. You got the racial slur. So there's also other translation examples I saw a bunch of that where you went from a gender neutral phrase or sentence, and after running it through the translator, you got a gendered phrase according to like a stereotype. So in order to build your intuition for why some of these things were happening, who here has, I want to get a feel for like how comfortable the audience is with word embeddings. Who here has used word embeddings in a project before? Okay, maybe like half the people. How many know how a word embedding is trained, like the pre-trained embeddings? Okay, maybe like a third. So we'll do a bit of a review for word embeddings. It's a dense representation of words. The idea for them was around since like the 1950s, and it's only practically been implemented in the last 10 years or so. Most of the word embeddings I've heard about are a hidden layer that was trained as part of another neural network in which the task was to predict words near other words. So it's all based off of co-occurrence counts. People toss around the phrase like, you will know a word by the neighbor it keeps or the company it keeps. Basically, it's like the neural equivalent of latent semantic analysis, or like doing a singular value decomposition. There's other techniques, but it's one of the hidden layers from a neural network that you then repurpose as an embedding layer for other models. So by the end of this talk, I hope that, like me, you'll have a better idea of why some of the examples I showed up top happen. And I hope you'll be able to recognize when something you are building is at risk of generating something similar, like bad results. And I hope you'll have lots of ideas about what you can do about it. So after like finding all those examples and submitting a talk proposal to here, I really lit a fire under me to just start researching stuff. The first thing that I noticed was people were defining particularly the word bias in many different ways. So when I said prejudice in my talk, I'm using one of the papers I'll talk about defines it this way as unwanted bias. And bias itself was really problematic. Like I found lots of articles, particularly with like technical people in the field, complaining about how journalists were covering some of those bad examples I showed up top and what that bias was. So I just want to like disambiguate bias from like bias variance trade-off, or how a statistician would define bias, like the average, like distance from the average prediction to the true parameter. Some of the more technical complaints about the journalism on those articles was that the journalist was complaining about the distance of the average prediction, not from the true parameter, but from an idealized parameter. And I was actually okay with that. Like, I think this quote really struck home for me with that in mind. And the ultimate goal is not building machines that think like humans, but designing machines that help humans think better. Like, I think we should be held up to the same standard that some of those stories focused on, and not like you can accurately represent that bias for what exists in the real world, but we have an opportunity to try and optimize to the ideal. So going forward, I'm using like the common definition of bias that most people on the street would use. I also found this one article by the Microsoft design team that kind of bucketed some examples of bias. And the examples I showed up top are an example of association bias as described in this article. And that's when data is used to train a model that reinforces and multiplies cultural bias. I do recommend that article. It's a nice grouping of different types of bias. So another thing I started seeing more and more as I researched was this. In my initial research, this was the most commonly cited source. And it is a paper in which they adapt the implicit association test to word embeddings. And what that gets you is it lets you quantify the unwanted bias, a specific unwanted bias, and it'll give you an effect size and a significance level. Also, this paper in general just gives a really excellent, it does an excellent job at putting the problem in perspective and asking bigger picture questions beyond just the technical questions of who decides which biases are unwanted, and calling out the need for other methods to be employed besides just the detecting and removal that we'll talk about. Another paper that was highly cited was this one by Tolga Balikbasi and others. But in this paper, they describe a way to remove specific biases by determining which of the many dimensions a word embedding has, which specific dimensions or some combination thereof represent a particular bias. They showed that they could collapse words in that combination of dimensions. So you can visualize this a little better. This is an example from another paper where they are doing the actual debiasing. And what you see is these are the two principal components of gender. So on the left, it's more male, and on the right, it's more female. So if a word in the bottom left, it's baseball, kings, rugby, lions, he, gaffer. On the right is female. There's princess up here. So what they've done is they've run a principal components analysis on a word embedding, and these are the top two components that explain gender. And then, so that's like the subspace that encodes gender over all the words. And then they've tried to collapse that. You probably can't see, but on the x-axis right in the middle here is 0. So that means it's not encoding male or female. And for all the words that should be gender neutral, but won't if they're biased, like receptionist or manager or babysitter, they've tried to move them to the middle of these two dimensions in the word embedding. But they've tried to leave gender where it's appropriate, like grandmother or sister. So for all the words that they thought were appropriate, they didn't move them, and the gender neutral ones got squished in. So that's what I mean by collapsed the subspace of that particular bias in the embedding. So the author of that Man is to Computer as computer programmer paper, Tolga, he has a GitHub repo in which he ran his hard debiasing method on Word2Vec trained on Google News. So you can play with a debiased embedding in terms of gender. And he posted an implementation of that debiasing code. And then Rob Spear and the people at ConceptNet, they also have a pre-trained embedding that they put out called Number Batch. And what they did was take it a step further, and instead of just doing it for gender, they did racial stereotypes and ethnic stuff. They removed lots of different biases. Here's some stats from Number Batch. So they compared all these different embeddings. Blue's Word2Vec, then you got orange's glove, another renormalized glove, and at the last two, purple is their Number Batch before they biased, before they ran debiasing, and the brown columns, these last ones, are after they ran their debiasing code. I don't think they did the same exact implementation that Tolga did with the last Word2Vec one, but they showed improvements, and they measured these correlation to stereotypes a little bit differently too. They didn't use wheat. They trained a they trained, I think they trained a sentiment classifier, and they tried different groups against it. So I also recommend this article also by Rob Spear. So I encountered this before I knew about the other pre-trained embeddings. This article also has really great examples of testing for bias in a statistically rigorous way. So I wanted to try that word embedding association test from that first paper on some of these other embeddings, like particularly the one that was hard debiased for gender by Bullock-Bosky et al. And I also wanted to try it on the number batch one that had been debiased, but there was no implementation of wheat I could find. And at this point, I really identify with this particular edition of this mean of fake O'Reilly books. So I just started writing code. I started implementing the word embedding association test. And I'll give an overview of how the test works. I'm not going to walk through the code too much because I think there's some other more valuable things to talk about. But the general way that the wheat works is you get a group of target words where these are groups of words you wish to test for the unwanted bias in. And then you get your attribute words, 2 groups each. So to test for gender bias, one group's man, one group's female. And you get lots of examples of those words. And the null hypothesis of the test is that there's no difference between the 2 sets of target words and their relative similarity to the 2 sets of attribute words. So in our example, to pick out individual words, it's saying male is about the same, male teacher is about the same as male nurse as far as cosine similarity goes. And then to put a p-value like significance on it, you should be able to, if that null hypothesis is true, you should be able to mix up the groupings of target words. And that's the crux of how they're doing the stats for this. It's a permutation test. So they're just mixing up the 2 target groups in every possible way. So to compare, for each word in our target group, they're going to compare the difference between that target word and each of the groups of attributes. And then they're going to do that for every word in each of the target groups. It's all based off of cosine similarity and just summing and averaging pretty much. So this gives you a test statistic. And then you do that for your original grouping of how I first laid out this example. And then when you do that for the original grouping, you can calculate an effect size, which is pretty much using your grouping things a little differently. Instead of summing, you're taking the mean and then you're just normalizing it to see how big of an effect. You're quantifying the amount of bias in this particular grouping. And then to get a significance level, you're just going to see how common it is. If you mix up those words in the target groupings, you're going to calculate that t statistic over and over for every combination. And then your p-value is just the number of times that a random grouping of the target words produces a test statistic that's bigger than your original grouping. So you might be able to see one.
So A and B are the gender words?
Yes.
And X and, what are X and Y? Is it some partition?
Yes, okay. Exactly. Okay. So this is all partitions. It's supposed to be all partitions of 2 equal groupings. That is.
So those are the Xi and Yi, right? So those are the indexes on the partition.
Yes, exactly.
What are X and Y what are the X and Y on the right side?
That's your original grouping.
Okay.
So it's like one.
Take the union of those sets of words and then you start partitioning.
Yeah, that's on the left. On the right is the original test statistic where it's the two original targets. So one problem with this you might see sticking out is cardinality is going to explode, right? Because if you have a long list of target words and you want to calculate a test statistic for every possible combination of two equal groups, yeah, that's going to explode. So I tried it anyway. It works pretty good. Like, my first attempts were very slow. I wanted to show a notebook. Let's see if I can do that. Oh, it's not going to let me here. Let's do this. There it is. All right. So let's see. I implemented Wheat. I did a Python implementation. The first ones were very slow. But then I realized it's doing the same comparison. Like you end up doing lots of cosine similarities, like the same ones over and over. So you can memorize those function calls and make this way faster. And that gets it to the range where you can reproduce some of the tests that they did in the paper. And in that paper I showed where they first defined Wheat, they replicated something, results from a psychological study or sociology study in which they measured implicit bias. So they tested for racial bias and gender, and I wanted to see if I could reproduce the results. So I loaded a bunch of embeddings. I used Glove. I also used a debiased version of Glove that used the same concept net type of debiasing code. And then I used Number Batch itself, their version of it, and I used Bullock-Bossi's hard debiased, gender debiased one. And then I ran the same tests that were in the paper reproducing the original research. And this plot shows p-values on the x-axis, and effect size is on the y. So the blue dot in the top left corner is like normal Glove. And the debiased Glove comes next. Number Batch did a little bit better. All of those had, Glove had an extremely significant p-value. And this, the debiased version of Glove, using the same debiasing technique that ConceptNet used on their Number Batch embedding, it didn't work as well as it did on their embedding. So just from differences in embedding, even if you use the same type of debiasing, you get different results. And then way in the bottom right corner is the Word2Vec trained on Google News by Bullock-Bossi that used the hard debiasing technique, which I think was a little bit different than what Number Batch employed. So this first test compares gender to science and art. And you can see the targets up here, how they're grouped. Science words are science, technology, physics, chemistry, Einstein, NASA. And the arts are poetry, art, Shakespeare, dance, literature. So that first paper I showed, they didn't choose this grouping. It came from original studies where they did this on people. And I was able to replicate the same effects and significant levels that they got both in the paper where they defined the word embedding test and the original psychological study that they confirmed. So I think the implementation works. And I did get to compare different embeddings, and I got to play around with different, let's see if I can get PowerPoint back. And I got to play around with different debiasing techniques. I ended up pulling out all of the ConceptNet code that they use to debias their embeddings. I took out all the dependencies, and I'll put it in the GitHub page that I linked so you all can play with debiasing whichever embedding you want. And the Wheat implementation is already up in that GitHub repo. So the takeaways I got from this was it works, but it's pretty noisy. Like if you then debias like I did glove, or you take number batch, and you try specific examples of generating your own analogies, or just looking at like two words and looking at the cosine similarity to see which one's most similar, like you do when you play with GenSim and the word similarity. They make it really easy. Even with the debiased embeddings, specific cases still gave really ugly results. So my main takeaway was you really need to experiment with these embeddings with text that is relevant to the task that you're using it for. And that's just echoing what they said in those papers above, especially the first paper where they define wheat. It should really be used in concert with other methods. It's not a cure-all at all. It does help, though. I mean, depending on your task, it can definitely be worth it. So far we've talked about building an intuition as to why you saw those original examples, because it's based on co-occurrence data, not a complex, I mean, it's supposed to be a complex understanding encoded in the embedding, but and we've shown a little bit about when it starts to happen. So I'm hoping you have an idea of when you should be looking out for this stuff. And we started to talk about what you can do about it. One thing is measuring your embeddings with wheat and in the context of how you're going to use it. And there's now a few tools that you can mess around, like playing with making your own target groups and testing for different types of bias. Now I want to talk about what else you can do, because the majority of the past couple months I spent researching this stuff. I found so many other things that you can do besides just using wheat to measure and collapsing a subspace along the dimension of a bias. And I think this other stuff is probably even more important. So it seems like there's a grouping that you can apply intervention in the to combat prejudice in text data, and it's at 3 different points in a typical workflow. So in this first part, we already talked a little bit about that stuff, and yeah, really knowing your data is going to help the most. Like, each of these embeddings has its own warts. The web crawl in particular includes a bunch of pornography, and as Rob Spear pointed out, Rob Spear's on the ConceptNet team and made number batch, words like girlfriend, teen, and Asian have a porn bias where like their semantic meaning is actually changed from what you would expect because there's so much pornography in the corpora in that corpus. So that can also implicitly bias other words related to those words. So you really have to pay attention to which corpus you're using to train an embedding, know if you're using pre-trained embeddings, which ones they use, and how that relates to the task you're using it for. A few good tools for like searching through large corpuses that I saw were flash text, which is basically a faster version of regex, and it lets you add really long lists of search terms and replace terms without getting an increasing runtime. Another good one is Bounter, from the same people that make GenSim, which is like a memory bounded counter that'll give you probabilistic counting over really big, like gigabyte size corpus. Another good metric you can employ at this first stage of like a data project is checking out gender pronoun gap, and that's just the ratio of the number of times he appears compared to the number of times she appears. So just as a quick overall metric on a big corpus of text, you can quickly test for gender stuff with gender pronoun gap, and people have done that on Wikipedia. So we talked about testing embeddings with wheat. Some of the ways that people have tested embeddings is wheat. They generate analogies. So that Bullock-Bossi paper Instead of using wheat, they used an embedding to try and find analogies, and then they had mechanical Turkers rate those analogies as offensive or not. And then they applied their method for debiasing, and then had them generate more analogies after they debiased, and had the Turkers rate them again to figure out what kind of effect they had. That was another strategy you can employ. And actually in that paper, in the appendices, they showed the form that they give the example of the form they showed to the Turkers. It's like perfect template for doing that for other types of bias besides just gender. So that's a good resource. Other people, like in Rob Spears' How to Make a Racist Algorithm Without Really Trying blog article, they trained like just really simple sentiment classifiers, so you can do things not just looking at cosine similarity, but like training just a simple positive negative sentiment, and then you can throw different text at it, like basically like that toxicity API at the beginning. And then I did see a couple of, like, there's lots of other formal mathematical ways to measure bias. A couple others I want to call out was also in Balak-Bassi's paper, where they define direct bias and indirect bias. So there are plenty of ways you can test embeddings. Now I want to talk about steps you could take when, okay, you've got an embedding, you did something to it, you're ready to train a model and use it. And most of these tools and methods to work on, like at this step in the workflow, focus on whatever the output of the model is and trying to see if it's fair between protected groups. So there's lots of great resources for this. People teach whole courses on what is fairness. That's a great one by Maurice Hart. There's lots of, there's a good syllabus and material in that reference for the course. Another good one to check out is Emily Bender's Ethics in NLP. A couple packages to help you test fairness and output. Again, all the slides will be posted. I'm going to start cruising now to get through the rest of the methods you can employ. This is definitely a good one to know. You should definitely learn about disparate impact, because that's one of the legal mandates in the United States, where there's an 80% rule of you cannot adversely affect one group of people of a protected characteristic more than another. And this is a great paper that talks about how do you actually do that. And there is a GitHub repo where some of that stuff is from this paper is implemented. This other source, there's an O'Reilly article about black box interpretation. And this article gives a great overview of different methods and when to apply them. It's not written in the context of assessing fairness or unwanted bias, but some of the methods they use you can apply to those two things specifically, and it's a great overview. One in particular is LIME, Locally Interpretable Model Agnostic Explanation. And for the Eli 5 package, you get a text explainer. So for any text classifier, you can analyze the input, like one specific piece of input to a text classifier, and figure out why it got classified one way or another, word by word. All right, now there's a whole bunch of other stuff that's more interdisciplinary that you can do to fight bias in a workflow. And two great sources for info on this is Abe Gong's Ethics for Powerful Algorithms. He's written a few blog posts on that, and he gave a talk at WrangleConf that went over it. And another one that just came out is the AI Now Institute's 2017 report. There are 10 simple rules for reasonable big data research, and it also emphasizes that this is an interdisciplinary problem, and it will take more than just technical solutions to fix this type of stuff, but it actually gives actions you can take. And it's just important to really think about how an algorithm can be technically fair but ethically lacking. Like when you're finished, or preferably as early in the process as possible, you should think about, if your algorithm, even if it's fair, who is it beneficial to? Who is it harmful to? If you're doing a classifier, what are the consequences for classifications in each part of the confusion matrix? Another area to really consider is how you market stuff, because the public's perception of machine learning and algorithms in general is they just don't have a good mental model for what it is. So I think we need to do better not overstating our abilities. And just to take one case study like the Perspective API, if this was marketed instead of toxic as just needs review, I think a lot of this could have been avoided. And not to pick on the Perspective API people, they've responded to this really excellently. They've published their analysis looking into that particular case where all those identity ones got toxic scores, and they've fixed the problem. They found a class imbalance problem in addition to using an undebiased embedding. So I recommend checking out their analysis of what happened to it. Also, text in general, outside of embedding, like you should have last mile filters. If you're generating text for a chatbot, there's plenty of tools to help you filter out bad words, and there's plenty of sources where you can augment those lists to make them a little bit bigger. Another thing you can do in the deployment stage is give people a good user interface that makes it easy to report inappropriate stuff. So here's just Google search results. If you get bad autocomplete, there's a place to log a complaint. Like if you don't give people a place, they'll go right to social media. So another thing that we need to be better at is accountability. And these are just two legal implications. Disparate impact, we talked about a little bit. But the other big one to keep an eye on is the European Union's general data protection regulation. And that'll affect any company that interacts with individuals in the EU, whether or not the company is located in the EU. That AI Now Institute report talks about specific things you need to be aware of within that as well. So just to summarize, there's the 3 steps, the 3 areas of a workflow, and the things we talked about in each. And I think that's where I'm going to stop so I can take a few questions.
Just a quick question about the 2 analytical attractions talked about. The first was a PCA, and the second was...
Sorry, I got a microphone.
Oh, sorry.
There you go.
Just a couple quick. You talked about 2 distinct analyses. I don't know. I wasn't clear if they were distinct. You had the PCA. Does the PCA inform the cosine?
PCA was used
They were in the
mainly for that visualization, so you could visualize the subspace that encoded the bias. But it's also used in the debiasing process when they're deciding which words need debiasing and which words are gender neutral.
Okay.
So they train like a quick SVM or something to say like, go over the whole embedding, and you give them examples of gender neutral words and non-gender neutral words if you're trying to do gender.
Right.
And they use PCA to pull it out.
Okay.
You can.
Gotcha.
Sure. Someone else?
I noticed back in the slide where you were explaining the debiasing, where all the words were sort of pulled to the center, there's a couple words still like left on either side. I was curious, like you had, I think, an arrow pointing to like the word president and one of the other ones, what that was.
Ah, jeez.
Sorry, that was super specific.
Yeah, no problem. While I look for it, maybe I can take one last question.
Can you make a plug for the talk with Lime in it?
The talk with Lime in it. Is there one here with Lime in it?
Yeah, like 340 and the...
Sweet.
Yeah.
Today?
Radio City today, yeah.
Okay, 340, Radio City today. There's a talk including Lime. So check it out. Definitely, that's a great way to do an explainer. Anybody else?
Yes, he has a question.
So if I want to debias, I need a list of words that I say these words shall be center. If I don't know the language coming into it, is there a way based on just the features of the text?
Yes. You give them samples of the types of word you want debiased. And that's what I was answering the question before is you train a quick classifier on yes, I want this debiased or no, I don't want this debiased. So it's going to make errors like this, that other question. Sorry, I can't do the split screen thing. I don't think I'm going to be able to pull it up. But that other question, he wanted to look more at that screen that had been debiased. That is from a paper, Chakrabarti et al. I can't remember the name of it. I'll sync up with you after. But yeah, it doesn't work. That classifier is not going to be perfect. Like that in that debiased one, it still showed president as like super male, and policewoman was still good, but that's still encoded bias. That was a good example out on the edges.
Okay, thanks everybody. Mike will be around outside.